atomic composition is not the only factor that determines the identity of a molecule. Some molecules have the same atomic composition, but have different three-dimensional structure. In our example here, malic and fumaric acids have the same composition, but the double bond blocks the free rotation about the carbon-carbon axis. Interconversion is prevented unless covalent bonds are broken. The two molecules are said to have different configurations. They are also called stereoisomers. Malic acid, with its two bulky groups represented in purple on this diagram, are on the same side of the double bond, and this molecule corresponds to the cis configuration. Fumaric acid, with its two bulky groups on opposite side of the double bond, corresponds to the trans configuration. A double bond is not a prerequisite to have configurational isomers. Molecules with the same composition and containing a chiral center can also exist in different configurations. So what is a chiral center? It is a place in a molecule where a carbon is bound to four distinct chemical groups. In our example, the chiral carbon is linked to one hydrogen and to three distinct chemical groups, R1, 2, and 3. If the carbon was linked to one hydrogen, to the group R2, and to two identical groups R1, the carbon would be said achiral. Depending on how the four groups are arranged around the chiral carbon, different configurational isomers are formed. Once again, a switch from one configuration to another requires the breaking of covalent bonds. The two different configurations of a molecule containing a chiral center are called enantiomers. Enantiomers are mirror images of each other, as you can see on this diagram. No matter how you rotate the original chiral molecule, you never obtain its mirror image without breaking covalent bonds. In contrast, you can obtain the mirror image of an achiral molecule by simple rotation of the chemical groups. This is a similar concept to our hands and feet. As you can see on this diagram, our feet are mirror images of each other. Now, take a look at my hands. If I show you the palm of my two hands, they are mirror images of each other. My thumbs point toward each other. I need to rotate one of my hand to have my two thumbs pointing in the same direction. But now you can see the palm of one of my hand and the back of the other hand. I would have to cut, rearrange, and glue back some fingers to show you the palm of my hands and have my thumbs pointing in the same direction. And I'm not ready to do that. So what are the biochemical consequences of having molecules in different configurations? The interaction between ligands and their receptors in cells are stereospecific. Molecules with the same composition but different configurations bind to different receptors, thereby increasing functional diversity. In our example, R and S carbon are two enantiomers and are mirror images of each other. They bind to distinct receptors on nerve cells in your nose. The binding of R carbon to its specific receptor leads to a sensation of a fresh spermine smell. The binding of S carbon to its specific receptor leads to the perception of a pungent caraway smell.
So double bonds don't allow any rotation, but what about single bonds?
Single bonds do allow free rotation. The different spatial arrangements of a molecule caused by free rotation are called conformations, not to confuse with configuration. The switch from one conformation to another does not require the breaking of a covalent bond. In theory, molecules can adopt an infinite number of possible conformations. However, some are more stable than others and become prevalent. Take this molecule of ethane, for example, and consider two of its conformations shown on the graph. These conformations result from a rotation of a methyl group, CH3, about the carbon-carbon bond located in the center of the molecule. The graph shows the potential energy of these two extreme conformations, one having the hydrogen eclipsed with one another, one having the hydrogen staggered apart. Due to steric hindrance, the staggered conformation has a lower potential energy. As we learn, it means that the staggered conformation has a higher stability than the eclipsed conformation. The free rotation gives flexibility to biomolecules and allows biomolecules to reach their most stable conformation.